Okay, hello. Today we're going to get back into forces again. We're going to be talking about friction. Now, friction is a different type of force, and we've dealt with it already this year, but we've just kind of solved for friction. So now we're going to get more specific and talk about exactly what the frictional force is. So if you take your hands and you rub them together like this, you're going to feel heat, and heat is a result of friction. If you take your hand now and rub it like away from you on the desktop that you're sitting at, you're going to feel some sort of force that's resisting its motion forward. So your hand is moving this way, but you're going to feel some sort of force that's kind of holding your hand back. If you were to use that same force over like ice, you'd find that that resistive force is going to be less. If you were to do it over something like rubber, it's going to even be harder to move your hand, so the resistive force is even going to be greater. Well, that resistive force, which resists motion, is called friction force. We're going to be talking about two types of friction force, static and kinetic. First off, we use little f, so it's the force of friction, or sometimes you'll see, and I'll go back and forth, to a little cursive f, and that sometimes helps us a little bit because you'll see later on where we're going to have kinetic and static that we have to kind of decipher between the two. Well, the two types of friction force are static and kinetic. Static means something's not moving. So if you have a static situation, this car right here is static. It's just going to be sitting right here. Kinetic over here is kinetic, meaning it has motion. So later on we'll be talking about kinetic energy, energy that has motion. So the two types of friction are going to be F, and this is what I told you that maybe it's easier to use a little f because here we have F of friction static. It's easier to do little fs. And here you have force of friction kinetic or little fk. Okay, so those are our two types. Kinetic, the object has to be moving, and static, it's not moving at all. Okay, so if I were to draw a free body diagram of an object, in this case it's a box, and I'm going to be pushing on the box. So I'm going to be pushing, and we're going to assume that this box is really, really heavy, and I'm going to be pushing and pushing, but it's not moving. That box right now is so heavy that I can't seem to get it moving. And the force of friction is still acting on it. That's what's preventing it from moving, because we talked about last chapter that every force has an equal and opposite force. So if I'm pushing over here and the box isn't moving, there has to be another force opposing that push, and that's our force of friction. So our push is going this way, and our friction is going to be going in the opposite direction. So the way that I look at it is the friction is going to go in the opposite direction that the box would move if it could move. So if I pushed here, the box would move that way, which means friction has to go that way. Even if it's not moving, it's which direction would it move if it could move. Okay, so if we talk about F net again, meaning the sum of all of our forces, we have the push force, which is in the positive x direction, and the friction force, which is in the negative f direction. Well, it's not moving. You're pushing, pushing, trying to get it to move, so the motion is zero. That means that it's static friction. There's no motion. Now, friction still exists even though the thing hasn't moved. So if you've ever tried to move a heavy piece of furniture, you kind of push at it and push at it, push it, it doesn't move, and then all of a sudden it kind of gives. As soon as it gives, then it seems to move a little bit easier. Then we get into kinetic friction. Once that gives, and now you have motion. So we're going to be having the exact same diagram here where you have F push in the positive x direction, F friction in the negative x direction, but in this case it's going to equal mass times acceleration. This is our kinetic friction. So which one of these is larger? Is it going to be static friction or kinetic friction? So think back of moving some heavy piece of furniture. Which is harder to push? To get it started moving or once it's started moving? So I don't know about you, but a lot of times I push really heavy and then all of a sudden it gives and then it gets easier. So that's telling you that static friction is much greater than kinetic friction. The force of friction is less once an object starts moving. Okay, so we're going to talk about what's called the coefficient of friction. we use a Greek letter mu, and it kind of has this, it's kind of like a cursive M, but it's mu. Okay, and this is the coefficient of friction. The coefficient of friction depends on the material of the objects. Now, it has to be two objects. So if you have a car going around a tar road, it's going to be based on the wheels in contact with the car, with the road. So if you have two hands rubbing against each other, it's going to be the property of the two objects that are in contact. So my hands would have a coefficient of friction between the two of them. Okay, if I were going to be ice skating and I would be on ice skates, the coefficient of friction will be between the metal of the skates and the ice. Okay, it is a unitless measure, and you're going to see this later that there's no units, there's no meters or newtons, it's just a number. The range that it goes between is 0 and 1. It's a decimal and it's positive, so you're going to get numbers like 0.32, 0.89, based on the materials. So if you can kind of picture ice and skates, metal on ice is going to have a very, very low coefficient of friction. And rubber from your car tires and the concrete on the highway is going to have a higher coefficient of friction because you don't want to slide. Okay, so this varies between 0 and 1. The other thing is that it depends on the normal force, and we're going to get into that with the equations. So right over here, the force of friction, kinetic friction, is equal to the normal force times this coefficient of kinetic friction. And I'll get into more detail in a couple slides. The static friction force is less than or equal to the normal force times the coefficient of static friction. The coefficient of frictions are specific for static and for kinetic, and they'll be specified in the problem what you're solving for or what you're going to be given that value. Okay, so let's try an example here. We have a 24 kilogram crate, so that's our mass is 24. Initially at rest, okay, on a horizontal surface. It requires 75 newtons of a horizontal force to set it in motion. So we have this huge box and someone's pushing on it horizontally straight with 75 newtons of force to set it in motion. So we're talking about static. It hasn't yet moved. Find the coefficient of static friction, which is mu sub s, that's what we call it, between the crate and the floor. So the first thing that I'm going to do here is I've got my free body diagram right here, and the forces acting are going to be my normal force, which is up, my force of gravity, which is down, the applied force, which is the 75 newtons. It's going to be the force is going to either be pulling or pushing, and then opposing this force is going to be the force of friction and the static friction that's going to be going in that direction. So here's our free body diagram. So what we want to do is we're going to find all the x components of the vectors and all the y components of the vectors and add them up. So we're going to start with y. Well, the only two forces that are acting in the y direction are the normal and the gravity. So here I have my y. I'm going to sum the forces, which is my net force is Fn positive minus Fg. And that equals to 0 because this object is not accelerating up or down. It's just standing still on the ground. So we can bring the Fg to the other side, and we know that the normal force equals Fg. Well, Fg equals mg. So all I have to do is multiply m, 24 kilograms, times g, 9.8. And I end up with the normal force is 235.2 newtons. So I'm going to hold that for right now, and now I'm going to do the exact same thing but in the x direction. And the only two forces that are along the x-axis here are my applied force and my frictional static force. So I have a positive force applied, which is this way, and the friction force is negative. So I have F applied minus the friction force. Well, we said that it's not quite moving yet. This is the force that happens before it moves, so MA goes to 0. So now I'm going to bring my static friction force over to the other side, and I have F applied equals the force of friction, static friction. Well, I have to remember from my equations of static friction that this equals the normal force times mu sub s. So knowing that, the normal force has to equal the, the applied force has to equal the normal force times mu sub s. So if I solve for mu sub s, I divide both sides by the normal force, and I have F applied divided by F normal. And now I plug in. My applied force is the 75 newtons over here. My normal force I got over here, which is 235.2 newtons, and it ends up to be 0.32. It's newtons over newtons. They go away. We have no units, and it is between 0 and 1. So 0.32 is going to be our coefficient of friction between the surface and the crate. Okay, so now what we're going to do is we're going to use the same example, but now the crate starts moving. So now we're going to be talking about kinetic motion. Okay, so once the crate from the first exercise is set in motion, a horizontal force of 53 newtons keeps the crate moving. So it takes 75 newtons of force to get it to move, but once it starts moving, it only takes 53 to keep it going. It's moving with constant velocity. That is telling us that our acceleration is 0. Find mu sub k, which is the coefficient of the coefficient of kinetic friction between the crate and the floor. So we know our applied force is 53 from right up here. We know our normal force, we got this from the previous slide. It was 235.2 newtons. We know the mass is 24 kilograms, and that was from the previous slide. We know our acceleration is 0 because it says that it's at a constant velocity. And we're going to be looking for mu sub k, which is our coefficient of kinetic friction. So what we're going to do is we're going to get all our x components. Once again, we know that the F applied minus the force of friction kinetic is equal to ma in this case. F applied minus the force of friction in the kinetic is equal to 0 because A is 0. So that ends up being 0. I move the F friction force over on the other side, and I end up saying that my force of friction, my kinetic force of friction, is equal to the F applied. Okay, well, we know what F applied is, but we don't know what the force of friction is. So remembering that the force of friction kinetic is equal to the normal force times the mu sub k, then we can find out what this is. So I'm going to replace my friction force with the normal force times mu sub k. So, and that equals applied force. I'm going to divide this by F sub n, both sides. I have mu sub k equals F applied over F sub n. F applied is 53 newtons. F sub n we calculated that from the previous slide, which is 235.2. And then I divide them, and I end up with mu sub k is 0.23. Now mu sub s was 0.32. The static friction is greater than the kinetic friction. Okay, so now we're going to kind of put everything together. Okay, this is our third and our last example. A student attaches a rope to a 20-kilogram box. He pulls it with a force of 90 newtons at an angle of 30 degrees. So now we're going to bring in our vector components with the horizontal. The coefficient of kinetic friction, which means it's moving, we have kinetic friction, between the box and the sidewalk is 0.5. Find the acceleration of the box. Okay, so this one is not constant velocity. It's going to be changing its velocity, and we're trying to find out what that acceleration is. So the fact that we're finding acceleration, we know we have to use Newton's laws. So if I draw a diagram right here, we have our normal force that's going up. We have our force of gravity going down. In this case, we have a force applied, but this is being applied at an angle. Okay, so right now that you see the angle, you're going to have to break it into its components. And then we have our friction force that's opposing the motion. So this box will be moving this way, which means our friction force is going that way. So step one, we're going to break any of our forces or any of our vectors into their components. The only one that's not along the x and the y axes is F applied. And we're going to break it down into its x. So F applied in the x component is F applied cosine theta. F applied in the y is F applied sine theta. Well, F applied is 90 newtons. and theta is 30. So all I do is plug that into my calculator. I have an x component of F applied, which is right here. This is my F, I'll just call it F sub x right now, and Fy is over here, and this is my y component of F applied. So I first break them up. The next thing what I want to do is I want to combine all my forces, so I'm finding F net. The easiest way when you have a lot of forces going on is just add up all the forces in the x direction, add all the forces in the y direction. So we're going to combine x components, and then we're going to combine y components to find F net. So I've made a little chart, and this helps me. I'm going to only look at my x components right now. So I'm going to be looking at any components or any vectors that are along this axis. Well, I have Fx right here, F applied in the x direction, and it's positive, and I have F of friction, which is negative. So these are my two. And then I'm going to do the same thing with the y. Well, what are my y forces? I have my normal force right here. I have F sub y applied, which is right here, and then I have negative Fg right here. So what I've done is I've made this chart. Now I'm going to add them up. So what I have here is F applied minus F friction. That's in my x, and all I'm going to worry about is keeping this separate. Now in the y, I'm going to have F sub n plus F applied in the y minus F of g in the y. So this is my F net in the x, this is my F net in the y. Okay, now we're going to go ahead and finish solving it. Okay, so step 3, we're going to solve for Fn. So this was my Fn, my F net in the y direction. And I have its Fn plus Fy minus Fg. And the object is not moving in the y direction, so we know that its acceleration is 0. So I'm going to bring the Fg over here and the Fy on the other side, and I have my normal force is Fg minus Fy. Remember, Fy is just your applied force in the y direction, the component. So Fn equals mg, because force of gravity is mg, minus Fy. Now I'm going to plug in numbers. The mass is 20 kilograms, the gravity is 9.8, and we calculated F sub y as being 45 newtons. And F sub y was just the 90 newtons times sine of 30. So if I do some calculations, I have my normal force right here of 151 newtons. So my next step now is I'm going to solve for my friction force. Well, I know that my force of friction is equal to Fn, the normal force, times mu. Well, Fn we calculated up here is 151 right here, and mu is a given number of 0.5, and so I calculate that, and now I have my force of friction. So now I have my normal force and my force of friction. I can go back in here, and this is my F net in the x direction, and we calculated this using our chart. So Fx minus F of friction equals ma. Well, Fx is 75, Fx was the x component of the applied force, which was 90 cosine 30, which ends up being 77.94. The friction force is right here, 75.5 is right there, equals m, which is 20 kilograms, times a. Our only unknown is our a value. So 77.94 minus 75.2 equals 2.44, equals 20a, and we divide by 20, and our acceleration is 0.122 meters per second squared, and it will be moving this way. So that's a really tough problem. We've taken vector components. We've also taken net forces, and we've taken acceleration into play. So that was consuming everything that we've pretty much done since the beginning of the year. Well, don't forget to do the assignment that goes along with this lecture, and we'll see you tomorrow in class.